Hello everyone, my name is Danilo Jodas. I am a postdoctoral researcher at the São Paulo State University, and in this video I'm going to present my work, which is related to the analysis of trees in the urban environment. And here we deal with the semantic segmentation of the tree trunk in the street view images of the urban environment by using a convolutional neural network. So first of all, I'm going to introduce the presentation's agenda, which starts with an introduction of the research area, and then I'll show the motivation of our research, followed by the description of the pipeline of the proposed approach for tree trunk segmentation, which is basically composed of three steps: the semantic segmentation itself, the results refinement, and the estimation of the central line of the trunk. And also experiments and results will be presented, followed by the final conclusions. So, in the context of smart city solutions, we can see several technologies that can be developed for the monitoring of the urban environment, such as the street lighting, traffic control, and the data acquisition for improving the air quality of the city. So we can see the urban forest surveillance as one of the most important solutions to analyze the green area deforestation and even the inventory of trees or their possible risk of falling, being this last procedure the main concern of many urban forest services and the public administrations around the world. But the tree analysis required the allocation of human resources to perform the calculation of several measures of the trees for further determination of their healthiness, which of course is an expensive and lengthy procedure because of the vast area of the urban landscape. And therefore, we need more efficient and automatic approach for monitoring purposes. So in this sense, we can use the support of several technologies to help expedite the entire process. For instance, the tree detection and also the tree measures estimation, including the employment of several image modalities like aerial images and remote sensing too, with the support of deep learning techniques like convolutional neural networks and also the use of image processing algorithms. So, in the literature, some works were already proposed, including the tree detection from unmanned aerial vehicles and Google Street View images using the well-known deep convolutional neural networks aimed to register a tree inventory, for instance. And also we have several segmentation-based approaches using semantic segmentation models like mask RCNNs and the UNet architecture, for instance, which is very similar to the methodology proposed here. But unlike the previous methods, in this work, we are more concerned with detecting specific part of the trees instead of the tree itself only. And here we can see the motivation of our research. So as I told before, considering the analysis performed in the field campaign, we can estimate several measures that support the tree analysis and also the prediction of the risk of falling. And in this picture shown here, we can see an illustration of two physical measures often acquired by forest analysts, the tree height and the diameter at the breast height, which is basically the diameter of the trunk, simply speaking. So the first one is quite simple to calculate if we have the top and the bottom part of the tree. But the diameter of the trunk requires an elaborate approach considering the point of view of the image analysis because we need to extract the right and the left boundaries of the trunk, and therefore we need a segmentation approach to extract the trunk region. But it's important to say that in this work is not aimed to predicting the risk of falling yet. But from the simple illustration, we can see the importance of handling each part of the tree separately. And in this stage of our research, we are more concerned with the detection and segmentation of the trunk region, since it's one of the most important structures considered in the fielding campaign. So specifically, we take the advantage of the deep learning techniques used for semantic segmentation to do that. Uh, so here I'm going to describe the pipeline of the proposed approach, which is composed of three simple steps. The first one regards the semantic segmentation by using a modified architecture based on the well-known UNet model, which receives the region that represents the tree trunk. And then the results are refined in the second step by using an image processing algorithm to remove the regions that belong to the tree trunk, which can be seen here by the small region in the upper right side of the image. And finally, we perform the extraction of the central line of the trunk by using a simple but efficient approach based on the average points of the right and left contours of the segmented region. Um, so here we can see an illustration of the architecture proposed for the semantic segmentation steps of the images, which is conceived to reduce the number of parameters of the original UNet architecture. So basically, it's a UNet model composed of encoding and decoding paths. So the main change on this architecture regards the use of deep depthwise convolutions in the encoding path and also in the decoding path of the UNet-based model. In the left side, the overall of the proposed architecture is illustrated along with the 2D convolutional block in the right side, which is composed of two sequences of depthwise blocks, and also a residual connection to avoid the well-known gradient vanish of deep architectures. Each block, each depthwise block is composed of two sequences of depthwise and one by one convolutions, batch normalization, and also the rectified unit activation function. So this conv2D block, we have four sequences of those operations, since we have two depthwise blocks in the conv2D block. So in the decoding path, we simply used one depthwise block right before the application of a simple transposed 2D convolution to restore the image resolution. So in summary, we simply used the UNet architecture and replaced the traditional convolutional blocks with depthwise blocks, but we can see that this simple modification helped a lot to reduce the network size. So considering the results refinement, the output of the CNN model is a probability map where each pixel has a value between 0 and 1. So the first step involves the application of the well-known Otsu thresholding using 0.5 as the threshold value, so we can generate a binary image in which the pixels of the trunk is represented by the white color. But some residuals may appear from this procedure, as shown in the bottom right of the second image of this figure shown here. So in this case, we need to remove them in order to maintain only the largest region, which is assumed as the one of the tree trunk. And to do that, we use the well-known connected component analysis to label each white region separately. For instance, the residual region could be labeled with 1, and the tree trunk region could be labeled with 2. And we have used a native connect neighborhood to check the connectivity of the white pixels. Then we simply take the connected region with the largest area and remove the residual to get the refined segmentation, as we can see in the last image of this figure. Okay? As the final procedure, we have to estimate the central line of the trunk by using the binary region obtained from the previous step. Here we have an illustration of the method that we proposed to estimate the points in the middle of the left and the right boundaries of the region in the binary image. So we have to firstly extract the points in both sides of the region, and then we needed to indicate which contour is the longest and which one is the shortest, so we can calculate more points for the middle line shown here in red in this picture. Okay. Then we apply a simple interpolation between each pair of points until we handle the last point of the longest contour. Here we take the last point of the shortest contour, and then we use it to interpolate with the remaining points of the longest contour. So, as I told before, we employ this approach to get more points for the central line. Okay. After that, we have to fill possible gaps in the central line obtained from the previous step. So here we have another illustration of the entire process. In the right side of this picture, we can see a central line with three disconnected segments. So to fill those gaps and link these segments, the first step involves identify the ending points of each segment as shown as small squares here. And then we applied again a simple interpolation between the nearest ending points of each segment in order to generate more points in these gaps. We see more examples of these procedures in real images in the results sections. And now I'll present the results obtained by the proposed approach. Here we have the results, some results considering all steps described earlier. So from the input image shown in the first column, we get the semantic segmentation results as shown in the second column, followed by the refinement in the third column and the overlap of the binary mask in the input image to highlight the area of the trunk. And it's important to note that the method performed well even in the presence of obstacles, as we can see in the third line where a car is in front of the trunk. And in the last column, we can see the central line for each example and the proper slope considering the direction of the trunk. The central line shown here as is shown here in white color in the last column. Okay. So, in conclusion, we have seen a combination of deep learning and image processing techniques for the segmentation of the tree trunk and its importance for the analysts in urban forest. And here we managed the segmentation with a CNN model which reduced its size and also with the refinement of the segmentation results. And for future works, we propose the improvement of the model by including more images in the training set. And also, we are designing the model for extracting the measures directly from the images by using the detected molding box. So that's it. Thank you for watching.